All right, so today looking at a new method for tackling second order equations with constant coefficients. This is called the method of undetermined coefficients. And again, this is part one of a kind of two-part lecture. Um, so we're going to specifically focus on functions that have this form. So again, you'll see on the left, we've got a constant coefficient equation. And on the right, we have a product of an exponential and a polynomial. And again, it can really help to think of the left-hand side as being like the system and the right-hand side as being the forcing function. Okay, so some external force to a spring mass dashpot system. Usually we have the right-hand side equal to 0. That results in the homogeneous equation. And that's a pretty easy equation to solve with constant coefficients. We know how to solve that. Now we're going to look at different scenarios where the forcing function has a different structure. So here, an exponential times a polynomial, which is a pretty general form. Something with exponential force multiplied by a polynomial. A polynomial can approximate basically any function that we care about. So this is a pretty important and substantial method because it can give us how to solve these types of equations. So we'll do that, and I'm going to show you kind of how this adds a layer of complexity that we have to deal with. It's not too bad, but there are some resulting things from our technique that we'll need to clean up as we go or recognize as we go. So let's tackle this equation here and find the general solution. How do we find the general solution? Well, we know in general it can be found by taking the complementary solution and then adding it to a particular solution. I recommend starting with this because this can actually shed some light on the rest of the problem. So finding the complementary solution to the homogeneous equation would be taking a look at the system, left-hand side, setting it equal to 0. And then we'll see, all right, characteristic polynomial here is just r squared minus 6r plus 5, which tells me that I have two real roots, positive 5 and positive 1. So that tells me that e to the x and e to the 5x are a fundamental set of solutions. So then my complementary solution will look like c1 e to the x plus c2 e to the 5x. So that's good to know. Again, the problem that we want to look out for is one of these exponentials that acts as a solution to the homogeneous equation, meaning turning the left side equal to 0, is that this function, okay, or is that this function? If one of the solutions to the homogeneous equation is this exponential or has this same alpha, then we need to treat it differently. Here we see it's not, so we're glad we checked first, okay? And we'll see an example of that in a bit. But now we want to go in and find a particular solution to this. So we'll treat it in a very, very similar way to that we've done before. We see we've got a product of a polynomial and an exponential function, so we'd hope that my y particular would be of the form e to the 3x times some function, we'll call it u. So let's just say u e to the 3x. And, in the back of our heads, we're imagining u's probably got to be a polynomial of some kind to go through all of this and end up as that, right? To go through differentiation and addition and then end up as a linear function. So we'll go hunting for u. Go hunting for u. This just writing it like this reminds us that what we're up to. So then that tells us that, well, yp prime must be u prime e to the 3x plus 3u e to the 3x, right? And then second derivative, I'm just going to do this in one shot, and you guys can pause and verify it yourself, but it should be u prime e to the u double prime e to the 3x plus 6u prime e to the 3x plus 9u e to the 3x. All right, so now I've got all my pieces, y prime, and y double prime. And so if I plug these into our dE, what should happen is that the e to the 3x's will cancel. And that's the goal, right? That we can just figure out what u must be. We assume that this function has a factor of e to the 3x. So we go back to our initial dE. Let's just write it down. And so we plug in what we've got. So y double prime for our particular solution is going to be like this. So u double prime e to the 3x plus 6u prime e to the 3x plus 9u minus 6 times y prime plus 5y. And that's just u e to the 3x, right? And so this equals e to the 3x all times 35 minus 8x. So as desired by design, all the e to the 3x's, since they can never be 0, are dropped off. And what we get on the left is u double prime. We see that the u prime terms cancel. Okay, and so we're just left with plus 9u minus 18u plus 5u. We get a minus 4u on the left. And that equals a 35 minus 8x on the right. Okay, so again, what we're hoping is that u is some function that was operated on by the second and first derivative, summed up, and it ended up as a linear equation. So if we assume and or hope that a particular solution for u would be some a plus bx, then what must have happened? Well, u prime must be b, which means u double prime would be 0. So that would leave us with, on the left-hand side here, 0 minus 4 times u must be equal to 35 minus 8x. And so we get minus 4a minus 4bx equals 35 minus 8x, which tells us that a must be negative 35 fourths and b must be 2. Therefore, u particular is negative 35 fourths, which is what, like 8.75 plus 2x. All right, so this is our particular u for our y particular. So therefore, y particular, which we said was u times e to the 3x, is of the form e to the 3x negative 35 over 4 plus 2x. So this is our particular solution. And we know that the general solution is yc plus yp. So that's c1 e to the x plus c2 e to the 5x plus e to the 3x negative 35 over 4 plus 2x. Okay, so that's everything going super smoothly well, and how we would tackle this in general. Now what I want to do is show you an example of when things get a little complicated because this exponential over here is actually a solution to the homogeneous equation, and how we deal with that. Okay, so what we've got here for our second example is it's the same equation, except for this piece. Okay, so the forcing function has e to the x up top instead of that e to the 3x. And so what we know about this is actually a solution to the complementary equation. Right, so our complementary equation we knew from before is c1 e to the x plus c2 e to the 5x. So since this is a solution to this, to the homogeneous equation, that means it's going to turn the left-hand side into 0 when we plug it in. So we're going to have to deal with that specially. So let's take a look and see how it goes when we look for our particular solution. So this kind of work is already done. I don't want to redo that. For our particular solution, again, we're going to hope that our yp, is it doing that, is u to the e times x. All right. So then that tells us that yp prime is that, y double prime, e to the x plus u e to the x. Right? So we've got our first, second, and third derivatives. When we throw these back into the original equation, we'll see what happens. So y double prime minus 6y prime. Y prime here is u prime e to the x plus u e to the x, and then plus y. Right, so what's going to happen over here is we will get u double prime e to the x. Let's cancel out all the e to the x's first. And we'll just be left with an equation involving u. So we'll get u double prime. The u primes, we get plus 2 minus 6. And that's it, right? So plus 2 minus 6 is minus 4u prime. And then we've got plus u minus 6u plus 5u. And that actually gives us 0u. So we drop the 0 term. And again, the reason that's the case, so actually, let's write this in here. So plus 0u equals 35 minus 8x. And this is because e to the x is a solution to the complementary equation. Okay, we know this because R1 was 1 and R2 was 5 from the characteristic polynomial. So since this is the case here, we have to deal with this a little bit special, and we'll see a pattern of a result. So the idea here, since there's no u term and we just have u double prime minus 4u prime equals 35 minus 8x, the idea is that that this u, if we let it be a plus bx, well, the u term is not going to show up in this equation, right, when we substitute it in. So we won't have that x term that we'll need for it to equal the right, because once we take the derivative, it'll just be 0 and then a constant. So that's the problem. So then if that's the problem, then let's say instead try up is 1 power up. We'll say it's ax plus bx squared. Or maybe let's even try, let's try this. Ax plus bx squared. Because then what that tells us is that up prime will be just a plus 2bx, and up double prime would just be 2b. So here now at least I have all the powers of x I need, which is just that linear piece. And this would actually work for this equation. So let's give it a shot and see. So I plug in u double prime 2b minus 4 times u prime. We said u prime was a plus 2bx equals 35 minus 8x. And then we distribute and rewrite. So we got 2b minus 4a for my kind of constant piece, and then a minus 8bx all equals 35 minus 8x. So that tells us that 2b minus 4a equals 35, and negative 8bx equals negative 8x. So the bottom one tells us that b must be 1. And the top one tells us, again, we're just mapping the coefficients here, right? Here must be equal to here, and here must be equal to here. So if b is 1, then I'll subtract this over. So that means that negative 4a is 33. So then again, a is negative 33 over 4 this time. And so therefore, my u particular is of this form, this negative 33 over 4x plus x squared, right? We have a bx squared from right here. And so it's of this form, or you can see it written in the book like this to kind of represent the fact that, hey, it's still got this product of a linear piece, but we need this extra x since the complementary solution was used on the right-hand side already. So therefore, if y is this u sub p times e to the x, then this ends up being x e to the x times this linear piece. Okay, so that's our y particular. And then again, your general solution is yc plus yp, and you can take it from there. But this is kind of a theme you can notice, is that, all right, if this e to the alpha x over here solves the homogeneous equation, then we can assume the solution is going to be of this form, where we have this extra factor of x, because we have to go a power up since this u drops off here. We have to go a power up to maintain the form of the polynomial when we differentiate twice. So this x is going to be here, and then you'll still have, you know, a polynomial q of x over here, which has the same degree as g of x, your starting polynomial. Okay, so that's in what page is that? 263? No, 253. It's like 252 to 255 in the trench text. So we'll do one more where we see two terms drop out because there's a repeated root in the characteristic polynomial. Okay, and before I cut out there, I was saying when we have a repeated root in the characteristic polynomial and this e to the alpha x is a solution to that equation. So that is the case here. So we've got a new equation, mixing it up a little bit. Here on the left-hand side, if we take a look at the complementary equation first for a little bit of insight, we see the characteristic polynomial is r squared minus 6r plus 9. And if we set that equal to 0, we'll get r minus 3 squared equals 0. So that tells us that we have a repeated root, r equals 3. So it tells us that my solution set is e to the 3x and x e to the 3x. Right. So then my complementary solution looks like c1 e to the 3x plus c2 x e to the 3x. So again, since this is the case, and that this is equal to this exponential, it's going to cause that cascading issue that we saw before in my u substitution, my variation technique. All workable, but we just have to be aware that we have to adjust what we're doing. And just like last time we had to bump it up a power, now we're going to have to bump it up 2 powers. Okay, so let's go looking for that y particular. We're hoping it's u e to the 3x still. And then from here, we'll get yp prime must be u prime e to the 3x plus 3u e to the 3x. Yp double prime is this here. So plus 6u prime again, plus 3u e to the 3x. There should be a 9 here. There should be a 9. All right. All right, so we've got yp prime, yp double prime, and y sub p. So let's throw these back into our initial dE. So all right, u double prime e to the 3x plus 6u prime e to the 3x plus 9u e to the 3x minus 6y prime is this guy, so u prime e to the 3x plus 3u e to the 3x, and then plus, what was it, plus 9y, so plus 9u e to the 3x. This all equals e to the 3x times this 4 plus 5x plus 6x squared polynomial here. So let's reduce some stuff. We'll drop the e to the 3x. We'll be left with u double prime over here on the left. We'll also see that the u prime and u terms all drop off, right? Plus 6u prime minus 6u prime. Plus 9u minus 18u gives me 0u prime plus 0u, all equals this this guy here. 4 plus 5x plus 6x squared. So then, since those dropped off, again, up equals a plus bx plus cx squared won't work. Right? Since they drop off in the middle here, because of this guy, that we need to go 2 powers up. All right, so essentially, you start here, and let's just this is just like a note here. So we start here, and we're going to integrate twice to find what u sub p should be. So u sub p will integrate this right-hand side twice. So you'll get what? 2x squared plus x squared over 2 over 3. It's going to be 5/6 x cubed. Plus over 3 is 2. Over 4 is 1/2 x to the 4th. Right, so that's just this integrated twice. When we take the constants of integration to be 0, because this is just a particular solution to this equation. Okay, and again, this can be rewritten as x squared times 2 plus 5/6 x plus 1/2 x squared. So now we see that this u sub p is x squared times some polynomial that has the same power as the right-hand side of the equation. Same degree. So then our y sub p is u sub p times e to the 3x. So that becomes x squared e to the 3x times 2 plus 5/6 x plus 1/2 x squared. So that's our particular, and then again, yc plus yp will be your general solution here. But this, obviously the tough part is coming up with a particular solution. And now you've seen the 3 different cases for this type of equation. Okay, when you have an exponential times a polynomial, if this guy is a solution to the homogeneous equation, just with a single root that this alpha satisfies, then it's going to be bumped up by a power. If this and this are solutions, it'll be bumped up a x squared. Actually, let's write this up in a better spot. So if it's not a solution, you'll be able to do it as we normally did in example 1. If it is a solution to the complementary equation, then this will be the form of your y particular. Okay, that we got to bump it up by 1 power. If e to the alpha x and x e to the alpha x are solutions to the complementary equation, then y particular is going to look like x squared e to the alpha x times some q of x. And again, the degree of q is equal to the degree of g for both of these. So again, you're going to need to go in and do the work to find that q, but this can be helpful in knowing how to attack finding those coefficients. All right. So this is how we deal with equations of this type. And in the next lecture, we're going to talk about when the forcing function has a sinusoidal input, so some sum of cosines and sines. Again, very similar in theme, but some particulars that we got to deal with. So I'll set you loose on some practice. Have fun, and we'll see you for part 2.